Okay, so we're going to be looking at what we started yesterday. And what we're doing is, where are the electrons in the atom? And that's what we started yesterday. Where are the electrons in the atom? And we kind of started by putting, the first thing that we started yesterday was we put the principal energy level, quantum level, down the side, which is represented by the lowercase letter n, and it is the row that the element is in. And so this is the principal energy level, or the energy level that the element is in, right? The first energy level that we're working with, right? The principal energy level is here, down the row. Principal quantum level is the technical term. And then the next thing we did was we looked at the sublevels. And so this is where this chart comes in, that is in your notes, the sublevels. So there are 4 sublevels. There's actually 5. They've discovered a 5th one. It is the G sublevel. We won't be working with it, but we're going to talk a little bit about it. It is the G sublevel. Now, you can see that the S, the P, the D, and the F. So let's label those. We did label those. So here is the S sublevel. It covers 2 columns on your periodic table, S. Then the P sublevel we put over here. It covers the 6 columns on your periodic table, the P sublevel. The D sublevel over here is for the transition metals, and then the F is way down here. And that actually covers 14 columns on your periodic table. So why does it cover this many? Well, the S sublevel has 1 orbital. And the reason that it's 1 orbital is because it's not actually considered to be an orbital. It's actually considered to be an orientation. So you don't have to write this down. I'm just trying to explain, and then we're going to do that tomorrow, all right? So the S sublevel has 1 orbital. It's actually an orientation, which should be centered on that axis, not lower. And it's a sphere. And so if you were to take a sphere and move it all around in all different directions, you would see that you can only have a sphere as a sphere as a sphere. No matter how you look at a basketball, it's always a sphere, right? And so this has only one orbital or 1 orientation. And so it is the S orientation. And because of Pauli's exclusion principle, he said an orbital can hold a maximum of 2 electrons. And so therefore, 1 orbital, which is the S orbital, it holds a maximum of 2 electrons. So the S sublevel has 1 orbital. It is the S orbital, and it holds 2 electrons. So therefore, your S sublevel umbrella is over 2 columns, 1 for each electron. Now we look at the P sublevel, which says 3 orbitals. The P looks like this. It looks like a dumbbell. That's what they call it, the dumbbell shape. And it aligns with the x-axis, and we call this the px orientation. So this is 1 orbital. And then there is a 2nd orbital that aligns with the y orbital, and so the y-axis, and so we call this the py orientation. So this is the 2nd orientation. The 3rd orientation looks like this. And it aligns itself with the z-axis, and the z-axis comes out of the paper and goes back into the paper, and so we call this the pz orientation. So there's 3 p orientations, or orbitals, 3 p orbitals. So here it is, 3 orbitals, the px, the py, and the pz. Now each orbital, thank you, Pauly, each orbital holds 2 electrons. So therefore, your p sublevel holds 6 electrons. That's why your p umbrella is over 1, 2, 3, 4, 5, 6 electron spaces. All right? Next, we look at your d. Your d has 5 orbitals. We don't look at the shapes because, I mean, you can look them up. They're complicated. They're very, very complicated. In honors, we only deal with S and P. So 5 orbitals. Each orbital, thank you, Polly, can only hold 2 electrons. So that's a total of 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the last one is the D. 7 orbitals, 14 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so that's how they go on. So one of the things that we want to notice is 1, 3, 5, 7. So if we were looking at the newly discovered D sublevel, how many orbitals would it have? 9. And how many electrons would it hold? 18. All right? Okay, but for right now, we're only looking at the S, the P, the D, and the F. So what we did yesterday was we then looked at hydrogen, which has 1 electron. We know this because it has 1 proton, so it has 1 electron. The way we want to map it out and say where it lives is we say the principal energy level, 1. Then we say the sublevel, S, and how many electrons there are, 1. So the hydrogen electron address is 1s1. And then if we were to do helium, we said we're going to move helium over into this space because helium has 2 electrons, and so both of those electrons would go into the S sublevel. Why? Because the S sublevel can hold 2 electrons, so we're going to put both of them into that 1s sublevel. It will then be full. Now, we moved helium from here to here. And the reason we did that is because helium is going to put its electron into the S sublevel. But why is helium over here? And the reason is because this column here is the noble gases, and there we call them full. The reason we call them full is because their energy level, their principal energy level is full. All of these P6s, 1, 2, 3, 4, 5, 6, all of these P6s are full. It's time to open the next energy level. Once you hit P6, you have to open the next energy level. But for helium, when you hit S2, because there is no 1P, see, there's no 1P, right? So when you hit 1s2, you have to open the next energy level. And so helium is a noble gas because it is full. That energy level is full at 1s2. So now we have to open the next energy level, so we call it full, and it is a noble gas. So let's look at carbon, which we did the other day. We said carbon has 6. So we're going to go 1s1, 1s2, full, helium. Now let's go to second energy level. 2s, we're going to put 2 electrons in there, and now it is full. We're going to skip the dip, and we're going to go to 2, second energy level, P sublevel, 2, and we're going to put 2 electrons in. So that will give us 6 electrons. So 1s2, 2s2, 2p2. Okay? Now let's do chlorine. All right, so we're going to do chlorine now. So I've got to do 17 electrons, and we're going to start with 1s, and we're going to put them in as 1s. And how many can I put in there? 2. And now that fills this, and I'm up to helium, so I'm full, right? So I'm going to go to the next row. 2s. How many electrons can I put in? 2, right? Now I'm going to skip the dip. I'm going to go over here. So I'm going to put in 2 into the second energy level. Now I'm in P sublevel. How many electrons can I put into the P sublevel? 6. Good. So now I'm up to 2, 4, 10. I have to put 17. Now by getting there, I'm at neon, which is full. I just hit the limit on the second energy level. So now I need to open the third. So that's why I'm at this this noble gas, right? So this is actually the electron configuration for neon, right? And now I'm going to open up the next energy level, 3. I'm here. So I have to put the first 2 electrons into the S sublevel in the third energy level. So now I'm going to skip the dip. And I'm going to go over to 3P. How many electrons do I need to put in there? 5. So now I count. 2, 4, 10, 12, 17. So that's it. That's it. How many electrons does chlorine need to be like argon, which is full? 1 more, right? If it's got 1 more, it will be full. That's correct. It would need 18. So if it had 1 more, then it would have the same electron configuration as argon, right? Does that make sense? It would be a P6, which makes it full like argon. Just 1 more electron and it would be P6, the same way as argon is. And every atom, listen to this, every atom on the periodic table wants to be like the noble gases. It's their golden life because the noble gases are the cool kids. All it wants in life is to be noble, like the noble gases. So if chlorine just had 1 more electron, it could be P6 like argon. And if it got 1 more electron, it would be an ion. And that's what's coming up next. Just getting 1 more electron so it could be like argon. See that? Okay? So it would have the same electron configuration like a noble gas. How many does carbon need to be like a noble gas? 4. That's right. But it also could lose 4, couldn't it? It could gain 4 and be P6, or it could lose 4 and be like helium, right? So it could gain 4 and be like neon, or it could lose 4 and be like helium, which is also a noble gas. Do you see that? So carbon has a choice, right? Okay? All right, let's keep going. Let's do germanium, number 32. Now, when you do germanium, there's a trick that you need to know about, another step. D is N minus 1. So when you get to D, it's going to be 4s2, but then you're going to get to D, which, by the way, is D10, right? Because there's 10 electrons, right? But the D is not 4D because the N is N minus 1. So it's not 4D, it's what? 3D, N minus 1. You see that? I'm going to explain why after we do it. But it's 4s2 and then N minus 1D. All right? D is N minus 1. So you're going to go 4s2, and then instead of saying 4D, you're going to go N minus 1. Here's N, N minus 1. We're in the 4th row, N minus 1. 3. Got it? Okay, go ahead, do germanium. I'm going to do mine way down here. Okay, go. Just go right along with the periodic table. Look at your boxes, look at your sublevel and your energy level. All right, here we go. 1s2, 2s2, 2p6. I got to open another one. 3s2, 3p6. 4s2, and then 3n minus 1 d10. Okay? And then 4p2. All right, now why is this 3D in this place here, and why does it drop back? So let's take a look at that real quick. So if I were to draw here my nucleus, right, there's my nucleus, and then I were to draw Bohr's orbitals, which you know is not real. That is not our current model, but it works as a model to explain what I'm about to show you. But it is not our current model. Our current model is the wave model, right? With the electrons jumping around so much that they make like a wave, a cloud, an electron cloud, right? Okay. So now I'm going to put in my electrons. So here is S1 and S2. 1s1, 1s2. 2s1, 2s2. 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. Now remember, before I keep going, remember that Aufbau said electrons go into the atom according to the lowest energy to the highest energy, which means that S1, 1s1 is the lowest energy, right? Lowest energy. That's what Aufbau would have said. That's the lowest energy, right? And then we keep loading according to as the energy is getting higher, which means as you go like this, the energy of the electrons is getting higher, right? Okay, so 2p6. 3s1, 3s2, 3p1, 3p2, 3, 4, 5, 3p6. 4s1, 4s2. So this is 4s2. Now the next one are the D's, right? So we're down here and we're seeing like 4s1, 4s2, 3d1. Well, according to Aufbau, that 3d1 electron has higher energy than 4s2. Because Aufbau says we load them in according to energy. So that 3d1 electron has higher energy than the 4s2. But what we've seen is that it does, in fact, load into the third energy level. But the periodic table shows that the 21st electron gets loaded in 21st. It actually gets loaded in after the calcium electron. It gets loaded in into the scandium electron, but it does have more energy than that 20th electron. So it does, in fact, get added in this way. The 3d electrons, they have more energy than the 4s electrons, and then next is the 4p electrons. So it is, by energy, it is this way, but those 3d electrons get added back into that third energy level. So this is, in fact, the way that the atom gets put together, but the 3d electrons do have more energy. So actually, there are 18 electrons in that third energy level, but those d electrons have more than this 4s electrons, okay? And that is very important, by the way, as in like which ones have higher energy. The 4s do not have higher energy because they get added in after. So your periodic table is your guide. It is your map. The highest energy electrons are the ones you just recently put in, not the most outer. That's a thing, the most outer. Those are important, but they're not the highest energy, okay? All right. Now, the next thing you need to remember is the F is n minus 2. So the D is n minus 1. The F is n minus 2. And so we're clear, they go here, n minus 2. So if you look up on that periodic table, or here, the F goes here, right? And then the D would go here. So what you would have in the 6th row is you would have 6s2. Then you would have 4n-1, F14, 5d10, 6p6. All right, 6s2, 4n-2, so 6 minus 2 is 4, F14, because there's 14 of them, and then D, n minus 1, 5, D10, and then 6p6. And then in this row, you would have 7s2, and then 5f, right? 5f14, n minus 2. And then you would have 6d10, because you have 6, right? N minus 1. And then 7p6. Back up to n. All right? So your n minus 2 and n minus 1 for your d's. Okay? Why? Because your f's are going to go back 2 energy levels when they get put in, and your d's are going to go back 1 energy level when they get put in. All right? So now we've done that. We've done all of this, the lettering, and we've put, we've laid out the map and everything else. But now what we need to do is we need to actually put the electrons in. So the way we do that is we use arrows, because the electrons are spinning, and that's no surprise. The electrons have a lot of energy. They're spinning in the orbitals, and they spin in 2 different directions. And by the way, all this is in your notes, and tomorrow as we go through, we're going to go through and review, because you're going to remember all this that we're telling you today, right? You're going to remember. So in your notes, clockwise, counterclockwise. Now, Pauli exclusion principle, part 2. The electrons must spin in opposite directions. Up, tomorrow we're going to write in clockwise versus counterclockwise, all right? They can be paired versus unpaired. So they have to be spinning in opposite directions. And so when we put them into the orbitals, we have to show that. If they weren't spinning in opposite directions, then they literally would like repel and throw each other out of the orbitals. So they have to be spinning in opposite directions. So, where's Hans' rule? So Hans' rule states, well, maybe it's not here. It's got to be here somewhere. Hans' rule states, the cake rule says all orbitals have to have 1 electron before anybody can get seconds. It's just the polite thing to do. The cake rule, you got to give everybody first before you give anybody seconds. The cake rule, right? You don't give like first, seconds, and thirds to one person and then turn around and go, yeah, sorry, there's no more. That's just rude. So let's see how it works. So helium, S, there's only 1 orbital. So we only put 1 orbital, right? Because there's only 1. And there's 2 electrons in it. So 1 is clockwise and 1 is counterclockwise. That's how we show those 2 electrons spinning. Very simple. All right, those are the 2 electrons spinning in opposite directions. Now let's look at carbon. Carbon, 1s, there's the 1 electron, the 1 orbital. 2s, there's the 1 orbital. 2p, how many orbitals should I draw? For p, for my p sublevel. 3. px, py, and pz. So you can see over on my chart, all the way on the end, p has 3 orbitals, px, py, and pz. So here they are, px, py, pz, right? X, y, and z. Now, according to Hund, I'm gonna put every orbital, every set of orbitals, every sublevel is going to follow the cake rule. So I'm going to start with the S, up, and then down. Did everybody get first? Yes, they did. And then they got seconds. 2 electrons. Up, down, firsts, and then seconds. Now I'm in the P sublevel. I only have 2 pieces of cake. up, up, done. But I want to be clear, I didn't do this, up, down, because that would be rude. See that? I didn't give first and seconds to the x sublevel, because that would be rude. Or the x orbital, that would be rude. So I gave first to x and y, and then I said to z, sorry, there were only two pieces, you know, but at least I gave two people first. Lindsay.
So you only go down after all three of them?
Yes. After all three of them. So we're going to do chlorine now. You'll see, okay? All right, so now we're going to do chlorine. We do 1 for the S, 1 for the S, 3 for the P, and you can go down because you don't have space. Now, what if I had a D? How many would I put? 5, right, okay. 1 for the S, 3 for the P, and here we go. I'm going to go up, down, because I have 2, right? P, up, and now down, down, down. Right, because I had 6. So up, down, because they're 2. Now, 5, so up, and then down, down. Now, why do we do this? Well, the reason we do this is because Hund's rule maximizes the number of single electrons available for bonding. I know this is in your notes because I remember typing this out. It maximizes the number of electrons that are available for bonding. And this is super important because here it is, maximizes the number of unpaired electrons. And that maximizes the number of electrons that are available for bonding. So if I had done it this way, here where there was an up, down, and then 2 blank empty orbitals, there would be no electrons available for bonding. But this way, there were 2 available for bonding. So it's very important because we need those electrons, because that is how all atoms bond with each other. So in this case, a question on a test might be, how many electrons are available for bonding in chlorine? And the answer is 1. There's 1 electron available. There it is. Okay? All right, let's go down to germanium. All right? So germanium, we're going to go 1, 1, 1, 2, 3, 1, 1, 2, 3, 1, 1, 2, 3, 4, 5, 1, 2, 3. Oh, Miss Paxton, there must be an easier way to do this. There is an easier way to do this. So there's a shorter method that you can do this called the noble gas method. Because remember I told you that all these noble gases are full? So if they're all full, you can go to the most recent noble gas passed. So in this case, with germanium here, the most recent noble gas passed is argon. So argon is 3p6. So what I'm going to do is go to here, and I'm going to say germanium, and I'm going to put argon into brackets. And that says everything is full up to argon. You can only go up to the noble gases. Okay? And then I go on from there. 4s2, 3d10, 4p2. And that is germanium. So now I can go 1, 1, 2, 3, 4, 5, and then 1, 2, 3. So up, down, up, 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 down, 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 and then up, up. So now the question is, how many unpaired electrons does germanium have? 2. 2 unpaired electrons, yep. And how many empty orbitals does germanium have? one empty orbital. There it is. There is the one empty orbital. And those are important questions. Hint, hint. Those are important questions. The empty orbitals and the unpaired electrons, because that is how germanium bonds with empty orbitals and unpaired electrons. So that enables germanium to bond. Okay? Got it? And what are the outermost, the valence, the outermost electrons that germanium has? The outermost. What's the outermost energy level? 4. The outermost energy level that germanium has is 4. And so germanium has 4 outermost electrons, 2 in the S energy level, sublevel, and 2 in the P sublevel. Do you see that? 2 valence electrons. That's what they're called. Four valence electrons. 2 in the S and 2 in the P. 4 in the valence, the outermost energy level. See that? Those are their bonding electrons. 4 bonding electrons. That's what's coming later. Next. All right? Okay. So tomorrow we're going to do the notes. Like, we're going to go through the notes and fill them in on all of this, and then we're going to the boards after the quiz. Got it? All right.